Okay, I want to talk about evolutionary reinforcement learning. I want to give an introduction at the beginning, and then I want to talk about two of the major topics in evolutionary reinforcement learning, which are hyperparameter optimization and policy search. To begin with, evolutionary reinforcement learning is the combination of evolutionary calculation and reinforcement learning. And it turns out that when reinforcement learning is dealing with an input space that is very large, turns out that it's going to take a very long time to be trained. So evolutionary calculations can help to speed up the process and find multiple answers for the problem. So the main steps of almost all evolutionary calculation algorithms are first initializing and creating a population of some candidates. Those candidates are the answers. So we're going to create a population, and this population can be anything. Can be hyperparameters, can be neural network weights, and in the next step we evaluate it with whatever metric weight that we have, and this step is leading us to the next step, which is the most important part. In the next step, two things are going to happen. We're going to pick one of those candidates as parents, and then we technically mate them, and then this mating is named crossover. After crossover, we're going to add some little randomness to it, which is called mutation. This step, we're creating next generation, which is named offspring, which is going to be replaced with the parents. So this way we're avoiding explosion in population, and also we are manipulating these candidates to a point that we find solutions. So, and this step is named variation. In the next step, we're going to repeat this process until a point that we see no progress in the population. This is an indication of that the population is converged. So we have some answers, so we cannot go further, or we can create some termination criterion as well to define where the process should be stopped. So I want to talk first about hyperparameter optimizations, and firstly I want to talk about Darwinian evolutionary methods. So Darwinian evolutionary hyperparameter optimization, or DHO, is actually the combination of machine learning and Darwinian evolution. So in machine learning, what we do is we manually fine-tune those hyperparameters, and this is usually done by trial and error, or sometimes if the person wants to find the optimum value, what we can do is usually what we freeze all the hyperparameters except one, and then iterate it with different numbers and create like a sort of a curve, see what is the extremum of that curve. But this method takes lots of time and energy and coding. But what the combination of evolutionary calculation with and machine learning does is that it offers an automatic way to find those optimum numbers for hyperparameters. So in this case, we consider each hyperparameter configuration as one of those candidates in the population. The first method that I want to talk about is Well, of course, the simplest way, the simplest algorithm can be the genetic algorithm that I talked earlier. We can just implement that, apply that to hyperparameter optimization, but with the difference that we're considering each candidate to be a hyperparameter configuration. So I want to talk about evolutionary strategy algorithm as well. So in this case, the main difference is that these hyperparameter, we consider these hyperparameters as vectors. We collect all of them in vectors, and we consider it as continuous real valued vectors. So this is the main difference from the previous algorithm. And the rest of the steps are almost exactly the same. The next algorithm is particle swarm optimization, which is very cool. Is very, very different from the rest of the evolutionary calculation algorithms that I've seen so far. So the first step is, again, representation, which we define how do we want to define the hyperparameter configurations as candidates. Next step, initialization. We do it randomly. We pick those hyperparameters as random numbers. Evaluation the same, but the movement. So this method, this algorithm is actually picked up from the movement of fish inside the sea. So how a group of fish swim together until reaching to the destination. Each fish is there is no like a leader or something in that group. Each fish is just moving with respect to its own position and its adjacent other fish positions. So here we define hyperparameters as vectors. So this is very beautiful because we can really represent them for instance, if we have like 3 elements, we can represent it in 3 dimensions. So we have these vectors, so we can define velocity and movement. So this movement has direction and magnitude. So what's happening is each one of these data points are different hyperparameter configurations, and each one of them has a movement, but this movement is adjusted with respect to each point's position and the closest ones. And this way we can update the algorithm by taking steps for each one of these candidates until all of them reach to, if the optimum solution is the star in this space, they all are going to eventually converge to that star. One of the beauties about evolutionary calculation is that at the end we have multiple answers. So it's different from reinforcement learning or other machine learning algorithms that always gives us just one answer. If it is converged, that's our answer. But the beauty of evolutionary calculation is that at the end we don't end up having just one answer. We can just pick different answers. So this is so beneficial. Why? Because it actually avoids subgame perfection or local optimums. Because if we have some answers which are local optimums, we can just switch. We can just change those answers because we have multiple answers. We can just change them and pick the one that is more promising and is the extremum. So determination is the same as well. The next algorithm is differential evolution, which is kind of expanding that crossover part of the evolutionary calculation. In the crossover, what we do is we just pick some parts of one parent and mix it with the other parts of the other parent. So this part is saying, well, this part is usually done like randomly or just by, manually by trial and error. But this part is talking about that in more details. It's saying instead of picking just random parts of one parent and mix it with the other random parts of the other parent, we can actually make something named trial vectors. We can kind of create all the possible crossover or mating scenarios, and well, of course, each one of these vectors have a difference from each other, and based on those differences and see which one is the fittest one and pick the fittest one. Why do we do it randomly? So this way it can actually it even speeds it up even more. So the thing is, in evolutionary calculation, there is no guarantee that the next generation is always better than the parents, right? Because maybe we made two great parents, but the next generation ends up being just terrible. So this is, this can happen in the previous algorithms, but here it is saying, let's make sure that the next generation that we're generating is the optimum possible mixture. So I want to talk about Lamarckian evolutionary. So I'm going to just talk about the overall algorithm to give big picture. What it does is, again, trying to automatically find the optimum values for the hyperparameters of the reinforcement learning. The thing is, there are two main differences in Lamarckian with Darwinian. So in Lamarckian, the idea is assuming like this idea is picked up probably from real nature. So what happens in evolutionary cycle of the giraffe? What happens is each generation not only is creating the next generation by a crossover and mutation, but also each generation itself tries a little bit to become better. So each generation tries to stretch its neck to reach out to the higher leaves. So how can we model this in reinforcement learning and evolutionary reinforcement learning? So it's pretty simple. What we can just ask after creating the offsprings, we can just ask those reinforcement learning models to optimize themselves, right? To find the solution, try to find the solution, try update them, try to train them, and then find the best hyperparameters possible. So we have some methods in reinforcement learning, just like proximal policy optimization, or PPO, or gradient-based optimization in machine learning. This way we can find, each generation can try to find an optimum value for its hyperparameters, and then transfer this knowledge to the next generation. So this way we are transferring that knowledge to the next generation as well. We do a little bit good, and then transfer that goodness to the next generation. This way it makes it conversion even faster. One thing about evolutionary calculation is that, well, one of the good points, one of the pros about, one of the cons of evolutionary calculation is that it gives us multiple answers, but The downside of it is that it usually takes very, very long time. It takes lots of iterations, or technically called um, generations. So the general algorithm for Lamarckian evolutionary is almost the same steps: initialization and evaluation. Selection is finding, the fittest agents, the fittest candidates as parents. So that's the selection. And then we have hyperparameter optimization, which is again a combination of two methods, both in reinforcement learning, trying to optimize the hyperparameters, and then doing the rest of the evolutionary calculation job, which is crossover and mutation until generating offsprings. And repeating is the same. So we have one third kind of approach, which is just a combination of the Lamarckian and Darwinian. So I'm not going to go too much into the details. I'm going to just talk about the next topic, which is policy search, combining the policy search part of the reinforcement learning with evolutionary calculation. So the very first one that I want to talk about is genetic programming. So let's not confuse it out with the first algorithm that I taught, which was genetic algorithms. Here we have genetic programming. So defining in reinforcement learning, policy is whatever function that maps states to actions. So whatever maps states to actions is policy in reinforcement learning. Like in most cases nowadays, this part is being done by neural networks or deep neural networks. So those weights of the neural networks can be considered as a policy. So it is suggesting that the population is going to be made out of those neural networks, in contrary to hyperparameter optimization kind of evolutionary reinforcement learning. So policies are here are represented as program structures, and so I have one example here. So this example is not neural network. It's decision. It can be decision tree. It can be any tree structure. So what it says is that, okay, now what we can do in the in the crossover and mutation part of the evolutionary calculation, when we are mating the parent, we cut one part of one of those policy program structures, which is policy. We'll cut one part of the policy of one parent and exchange it with the other parent. So we can see here, like, well, of course, again, policy is mapping state to the actions. So probably the end nodes here are actions. And probably the first node that's starting is conditions on states, just like a decision tree. And here it says, like, okay, I'm gonna, replace the start condition with this positive condition here, and exchange it, create the offsprings here. So this is the main idea. The rest of the steps are pretty much the same. The only difference is that we are considering policies as the population elements. The thing is, if we want to model this for neural network, what we can do in the crossover section, we can keep, for instance, a few first layers of one parent, and then adhere it to, like, say, the last 5 layers of the other pattern. And then we create a new neural network with new weights, which is the offspring, which is the next generation. So this is the main idea. This is the big picture. So, in summary, I talked about what is evolutionary reinforcement learning, and then I try to dive into the first two major subcategories of ERL, which are hyperparameter optimization and policy search. And I'm talking about those methods for now, but in the future, I'm going to cover more topics and talk about more details in evolutionary reinforcement learning. Thanks for watching.